So welcome everyone. Welcome back to this seminar on process calculus implementation in Isabel Hall. The process calculus is called the Thorne calculus, and it's a calculus we have developed here at IHK. So last time we have already looked at this very central notion of bisimilarity, which is a notion of equivalence of states in transition systems. And later these states will correspond to processes. So we have a notion of behavioral equivalence of processes, and bisimilarity is a rather strong notion, as I said. It's not just about whether two processes can execute the same sequences of actions, but it's also concerned about where non-determinism is introduced. So I brought this example. If we have two processes where one process can execute a sequence AB, where AB are some actions, the other one can execute AC. That's the difference whether both processes I was wrong. Sorry, it's a single process that can execute AB or AC, and there are two processes actually that have this behavior. So the first process will definitely execute A and then decide whether to execute B or C. The other one will first decide whether to execute B and C in the end, and then after the decision will execute A and then execute B or C respectively. And these are considered different according to bisimilarity. So in the label transition systems, semantics, you would have the meaning of the first process to be a state from which you can make one transition to a new state with the action A, and then you have a branch, right? And one leg goes with B, the other one with C. Or in the other case, you will immediately have a branch and both legs will be labeled with A and go to two different states. And from there, you have one leg each going further, one with B, the other one with C. And why this strong notion of bisimilarity as opposed to just looking at these paths, at these sequences of actions? Because it has nicer properties, and which we need in our development. For example, we want to reason in a modular way, that we can reason on components and say, okay, if we replace this by something that's bisimilar, then the overall system stays bisimilar. So let me quickly go through these diagrams again to refresh this a bit. So the core notion of this all is the notion of a simulation relation, as we have seen. So K is a simulation relation if and only if the following holds. If you have P and Q that are states, or more specifically later processes that are related by K, and P can make a alpha transition, a transition with the action alpha to some P prime, then we must then there must exist a Q prime such that we can go with this alpha from Q to Q prime, and the P prime to Q prime are in relation K again. And the bisimulation relation is, if it's, so to say, a simulation in both directions of K is a simulation relation, and the converse of K is also one, meaning that if you can make a step with Q to Q prime, then and have this relation K between P and Q, we must be able to make the step with P prime, P to P prime, and then have P prime and Q prime again being in relation K. So the bisimulation is very easily defined in terms of simulation, just simulation plus the converse is also a simulation. And now the bisimilarity relation is just the largest bisimulation relation. And this means we can also directly define it with a co-inductive definition, which we had here, showed this last time. And these rules reflect the simulation game that I just described. And then it's very trivial to prove that each bisimulation is included in the bisimilarity relation, which we have here. Each K, which is a bisimulation relation, is a subrelation of the bisimilarity relation, which is denoted by this tilde. So this is the central lemma that we would usually or naively use to prove that two processes are bisimilar, we just pick a relation K in which these processes are, and then prove that K is a bisimulation relation, so it must be included in bisimilarity. So these two processes that are in relation K are also bisimilar. However, this can be hard at times. And I mentioned this also a bit already last time, because what we would like to do is, if we have a bisimilarity lemma, for example, in our process calculus, something like for all processes S and T, we have that this S parallel T is bisimilar to T parallel S. And ideally, we would like to have our relation K to cover only terms, processes of this form, right? So this commutativity of parallel composition, and we would like K to be defined as relating any P and Q where there exist S and T, such that P is S parallel T and Q is T parallel S. However, apart from very simple process calculi, this doesn't work, because if you make a step with P, we can also make a step with Q, but we don't get P prime and Q prime that are again in this relation, where P prime has again this shape and Q prime is then the same with side swap. But you typically have P prime and Q prime that are not quite in this relation K, but that are in some relation derived from K, something like F applied to K. And if we want to do the standard bisimilarity proofs, then we have to extend our K, right? So K must now not only cover these S parallel T and T parallel S, but it must also cover these slightly different kinds of pairs of processes. But this means that we have to also consider them here on the left-hand side, and also for these, we have to prove if I make a step, I can make a step here. And then I get maybe into some processes P double prime and Q double prime, which are even less related in K, so to say, which are form some new kind of pairs, and we must also include them in our relation. And so we have to possibly extend our relation K very heavily and have to consider all these different possibilities that this extended relation covers. However, many of these things can be handled once and for all, or can be handled uniformly. And the point of these so-called up-to methods, to which we get today, is that we can handle once and for all certain such enlargements of or modifications of the relation K. So the goal is that it's now enough to prove this simulation property in a slightly different form, namely that P prime and Q prime do not have to be related by K, or are not related by K, but instead by some relation F of K, F applied to K, where F is a function from relations to relations. And the nice thing is that if this F has a certain property, which is called respectfulness, if this F is respectful, then proving this here, that K is a simulation relation up to F, so that we get into this FK related stuff here, that this is also enough to prove that K is included in bisimilarity, and therefore ultimately P and Q are bisimilar. So, and today we will in particular look at what this respectfulness is and why it's defined the way it is. Well, it is because this, in a rather clear way, shows that proving this variant of this, what we had above, is also enough to show that K is included in the bisimilarity relation. And because we have now this pattern here, that on the left we have K, on the right we have Fk, and in our proof that this proof mechanism is sound, we have to consider other combinations. Therefore, we have introduced this notion of progression, where we just say, okay, on the left we have some relation K, on the right we have some relation L, and whatever it is, and we call this progression, we say K progresses to L if and only if, from P being in relation with Q via K, and P being able to transition to P prime using action alpha. We always have that there exists a Q prime where Q goes to Q prime with alpha, and P prime and Q prime are now in relation L as opposed to in relation K. And of course, it's kind of easy to see that these above here are special cases. So K is a simulation relation up to F, just means K progresses to F of K. And it's a simulation relation without any up to, it means K progresses to itself. And of course, simulation relation is also a special case of simulation relation up to, because K is a simulation relation if and only if K is a simulation relation up to identity. And as we will see, we take F to be the identity, then this should be sound, this proving up to, because it's then the same as what we have above. And actually the identity function has this respectfulness property. Okay, are there any questions about this part? Okay, then let's look at what we have here in the code. So we're at this position here where the red cursor is. Now we go to the definition of what a respectful function is. So it's about these functions F, for which we can know that the up to method of proving by similarity is sound. So if you prove that K is a bisimulation up to F, so the simulation game works in both directions, bottom up and top down, then K is included in the bisimilarity relation, and therefore P and Q are bisimilar. And sound is a function F whenever this holds, that the K is in the bisimilarity relation after we have established this property. But respectfulness is a more specific property. It's, so to say, a criterion for soundness. So they are probably sound, I think they're basically always, except for maybe trivial settings, there are sound functions F, for which this up to is sound, which are not respectful, but we are only caring about respectful functions F here and prove that these are always sound, because respectfulness is something that for the cases we want to consider is relatively easy to prove. In fact, we will soon have a look at some basic lemmas about respectfulness, that certain basic relations are basic functions are respectful and certain operations preserve respectfulness. And then for our practical cases, we will most often be able to just show respectfulness by applying these lemmas, and this is even automated in our development here. Okay, so what would be a sensible notion of respectfulness? So a notion where we can disprove the sounds very easily. It's in fact not this yet. It's this one here. So maybe I will start with this respectfulness here below, which refers to this so-called shortcut progression, but maybe I will introduce first a slightly stricter notion of respectfulness and later get into the full story here. So maybe ignore the part on the top for now and just look at this respectfulness definition below and pretend that this squiggled arrow is not a squiggled arrow, but that it is this arrow here. Right, so this is the bilateral progression that we saw before. So it corresponds to this diagram here. So K progresses to L, as I said, if from this relation and this transition, I can conclude there must be a Q prime such that you have this transition and this relation holds, so to say. And as I described previously, it's defined via operations on relations. So we take the converse of K and L. So that's now about relating Q and P and Q prime to P prime. And we say K progresses to L if and only if, by definition, the composition of the converse of K and transition via any alpha is a subrelation of the composition of transition via this alpha and the converse of L. So if I can go this way from Q to P via P prime, making the K step in according to the converse of K, then I must be able to go also to the right and then to the top. And this is what we had here. That's the unilateral progression, which is a generalization of a simulation. And this is what I just said. For all alpha, we have the converse composed with a transition in the original transition. So we have the possibility that the transition systems are different. Right? This must be included in the transition of the simulating system composed with a converse of L. The bilateral progression is the generalization of bisimulation relation, and this is just, okay, K bilaterally progresses to L if it unilaterally progresses to L, and if the unilateral progression also holds for the converses, converse K to converse L. And now take this notion of bilateral progression, and this is now what you first should think of here. So think that this would not be this squiggled arrow, but bilateral progression. And what this says is now a function f from a relation to a relation is respectful if and only if there is this preservation property holds, right? So if we can progress from K to L, we must be able to progress from Fk to Fl. And the proof why from this the soundness follows will come later, but I will want to give you at least some sort of idea why it's exactly this preservation property that we are interested in and it works. So say we want to prove bisimilarity using an up-to method. The concrete up-to method is characterized by this F. So we prove that from this P related to Q and A and K, relation K, and this transition, we can conclude that there exists a Q prime such that we can transition, and these two guys on the right are related by F of K. Now, in order for P and Q being bisimilar, we must have the following. Whenever I make a step with one of them, Q or P, I must be able to make a corresponding step with the other one, such that I get into two processes where, again, if I make a step with one of them, I can make a corresponding step with the other one and get into processes where, again, and so on. But here, we know the first two processes are in relation K, and we have proved that if I make a step with one, I can make a step with the other one, and I end up in relation F of K. And that's kind of not so good, because now we know P prime is related by Q prime via F of K, but for things that are related by F of K, we don't have anything directly proved. We have proved something for processes that are in relation K. However, what if we have now such a preservation property, right? From K progresses to L, we know that Fk progresses to F of L. Well, then we know that if we have proved that K progresses to F of K, that also F of K progresses to F of K, right? So we have something for f of k. We can progress from k to f of k. This is what we have proved. From this, we know that we can progress from fk to f of k. But if you know this, then we know also from f of k, we can progress to f of k, and so on. So, and this means we can continue this bisimulation game. Right? So we know these are related in k. We can progress to f of k. We can progress to f of k. We can progress to f of k, and so on. And we can go on like this forever. And this maybe intuitively tells us already that P and Q are in fact bisimilar. And this is why this preservation property is a good one. It guarantees us that we have the P and Q are bisimilar if we have established this up to bisimulation. Okay. Is this yeah?
Why? So so why do you need this? What is it by? So this I forget the name. The progression in both ways, basically.
The bidirectional one.
Yes.
Well, ultimately, we want to prove bisimilarity, which allows us, or which forces us, or which includes the statement that we can go in both directions. So two processes are bisimilar, so if and only if we can take any of the two and make a transition, and then the other one will be able to simulate it. And we get again into processes that are bisimilar, and then we can do the same again also in both directions. So at any step, we can take either of the sides, either of the processes, make a step, and the other must be able to simulate. That's how bisimilarity is defined, and in particular, this makes bisimilarity a symmetric relation. Right? There's also the notion of similarity, which is the largest simulation relation, but it's a much weaker notion. And bisimilarity is what we typically want to use here.
Okay, so then basically, if you use regular progression, I assume you would get similarity instead of bisimilarity.
Yes, I think so.
Okay.
We should get the similarity, yes. I think it will work out also with the up to. I have not thought through this, but I think it will. So similarity is the largest simulation relation. So definitely, if you wouldn't take this up to approach, but this easy approach that you see on the top, then you would get similarity. Any more questions? Okay, so then let's look at the code again. So I think I've now kind of motivated why we want to have such a preservation property, that if we have a progression here, we want to have the progression with from f of k to f of l. However, now you see that this is a different arrow, it's a different relation, a different notion of progression. So far I have said, okay, we just take the bidirectional progression and that's it. However, in reality, we take something that's called a shortcut progression. And yeah, I maybe go first through this, what we see here, and explain a bit what it is and why it's called shortcut progression, and then I will give you a motivation why we want to have that. So shortcut progression is now denoted by this squiggled whatever arrow. It's again a relation on relations, right? And it's defined like this. So the shortcut progression is, well, that's a meet, right, in the lattice of relations. So if you take consider relations to be sets, then it's the intersection. So it's the meet of the inclusion, the relation inclusion, and the actual bidirectional progression, right? And what does this represent logically? Well, K goes via shortcut progresses to L. So if I would write this out here, I could write it out as a lemma, because actually it is a fact, right? I could say K. How was this arrow now? Let's copy it. This must be the same as K smaller equal L, so it's included in L, and so the AND is the logical correspondence to this meet. It's the meet in the Bool lattice of the Booleans. So like this. So this is how I could have defined it as well. I just took this point-free style because I like it more to think of relations as just some first-class entities which you can compose. So that's now the non-point-free thing. And it should actually follow from this thing which is automatically invoked by the simplifier. So I probably can just say I prove this with a simplifier. And yes, Isabel has established that this is a fact, right? It's just directly used this definition and then some trivial reasoning using, in particular, this definition of the meet for the lattice of Boolean functions or functions to the Booleans. So the progression is this kind of shortcut progression we have if either there's a real progression from K to L or K is simply included in L. And where does this inclusion come from? Well, let's look at the diagrams again. This inclusion is the part that this shortcut refers to. This is because of the following. If for a while we think that this transition, or not just for a while, if you consider this transition to make no step really, right? So this transition goes from P to itself, and from Q to itself, and from any process or state to itself, then progression actually means inclusion, right? If P and Q are in relation K, and I can go from P to a P prime via, well, the identity or the equality relation, right, where we only have these little loops from every state to itself, then the P prime is obviously equal to P. And progression now says, okay, if we are in relation K and P is equal to P prime, then I must find Q prime, which is equal to Q, but it's Q itself only, right? Such that P prime is in relation L to Q prime, but since Q prime and P prime are now equal to the things P and Q on the left, what this says, if the transition is just the equality, is that if P is in relation K with Q, P must be in relation L with Q, right? And this means K is included in L. So the inclusion relation, K included in L, is a special case of a progression, namely where transitions are with any action alpha are precisely possible from each state to itself. So where the transition relation with any alpha is just the equality on states. Is this clear, or are there questions?
So do you use this to make the proofs easier?
No, I actually use this to make certain proofs possible in the first place.
Oh.
And so I will get to this. So it's about the so-called proofs by the method up to context, because there it can be that in certain situations we are not able to make a step to another state, but we stay at the same state or stay at the same process. And for these cases, it's important that we cover this equality case as well.
Okay, so but would progression be enough to prove, or like this, I forget the name again, by progression, to prove by similarity, or do you need the short like this extra property to prove by similarity?
Well, it depends on what concrete up-to methods you want to use. So the concrete up-to method is what's characterized by the f, by the function f that you pick. If you do not want to use this up-to context, but you are fine with the ordinary biassimilation proofs where f is the identity, or by similarity proofs up to bisimilarity, where you don't require these guys to be in relation K, but to be bisimilar to processes that are in relation K. For these simple up to methods, it would be enough to just take the ordinary bidirectional progression. It's only the up to context where we really need the more complicated one. In fact, I made a note I can show you. I have here the notion of a mutation system, which is a slight generalization of this up to context thing. And at some point, I have this little comment. Now, where is it? I cannot find it now. There must be a comment somewhere. Because it's the weak mutation systems, huh? See. Here, this is the comment. This is the place where we finally need the extra condition. K is included in L that sets apart this squiggled thing from this ordinary bidirectional progression. Here, in this lemma, this little lemma, this is where we find it, basically the only place where we need it in the end, but other things rely on this lemma, of course, right? So it can be really nailed down to this one point. And if we drop this mutation system stuff for the up to context proof methods, so we drop in particular everything that relies on this lemma, then everything else would also work with the ordinary bidirectional progression.
Okay, thanks.
Okay, so the important first message is really that the inclusion relation, K included in L, for example, as a concrete application, and that this inclusion relation is a special case of progression, namely for the case where both the original and the simulating transition system are defined such that for any process or state P and any alpha, I can make a transition from P via alpha to P itself and nothing else. So the transition system where the transition relation applied to any alpha is partially applied is the equality relation. So okay, and this is, one moment, yeah, okay, here we were. So no respectful functions. Okay, so this is was just exploration. I will remove this again. And now what do we have? This was our definition of respectfulness. It now uses this derived notion of shortcut progression. And shortcut progression means that something shortcut progresses, so to say, from K to an L, if and only if K is included in L and K progresses to L. So it must progress to L via our given transition systems, but it must also progress to L via this equality transition system. And that's the important thing. And this is what this comment says here. Right? So we choose the term shortcut progression because inclusion is just bidirectional progression for the case that the original transition relation partially applied to any alpha is the equality, and also the simulating one partially applied to any alpha is equality. Should maybe say some, no, okay, it's okay. And furthermore, equality is just the original transition applied to alpha to the power of 0. So that means to the power of, so it means 0 steps, right? So relation to the power of 1 would be the relation itself. Relation to the power of 2 would be relation composed with itself. And likewise for 3 and 4. So you have these longer and longer compositions. Of course, the relation to the power of 0 is just the identity or the equality relation. Right? So inclusion is progression for the case that these guys are actually equalities, and because the equality is just the actual original or simulating transition. Oh, this should be the other one. Because the actual 1 to the power of 0. So intuitively, equality means taking 0 steps. This is what it says. Therefore, this term shortcut progression is mandated because it's about no steps, so to say. I thought shortcut progression would be a good catchy name. And this argument, which I have made informally now, is made formal in the following note. And now we get to a new nice Isabelle construct, the notepad. The notepad just opens a proof context or gets you into a proof context. You say notepad begin, and at some point comes an end. And here you are in the situation that you can just conduct a proof. The difference to, so this is actually this ESAR proof language, the structured proof language that you see in action here, which we have seen kind of in action before. It's just that these proofs were all very primitive, and so you couldn't see it very nicely what it is about. Here we have a very little proof that uses this language, and this is also such a proof. However, unlike when stating a theorem or lemma, with Notepad, you don't have any goal to prove. So we see the part below here is empty. So there's no goal to prove. So we can make certain proof steps, but in the end, we don't have to draw any conclusion of this. So Notepad is really only to make, so to say, formal machine-checked comments, proof comments in your code. You don't prove anything that you will use later, but you just make some statements and show that you have a machine check of their truth. So, and now now it gets a bit tricky. So let us get quickly to the top, what we had here. And the point I want to make clear here is that we are working in the context of a so-called locale. This locale, as I have said, establishes basically some sort of algebraic structure. We say a simulation system is characterized by an original transition and a simulating transition that have these types. And then we have begin, and then we are in the locale context. So starting from here, we can refer to the original transition and to the simulating transition also via their notation here. And everything that we have developed here always assume that there is some original transition and some simulating transition. And at some point, the locale context will be ended. And then we have a whole development that is only, so to say, valid under the condition that you have these things, these two transitions given. And then we can interpret the locale, which is a kind of instantiation. And we say, okay, now we take a particular simulation system by fixing the original transition and the simulating transition, and then all the definitions and lemmas and theorems you have established here will be specialized to this particular case. And now we do something tricky here, where I was delighted that it works. We do such an interpretation here. We say we interpret the simulation system for the special case that both the original and the simulating transition are this actual original or simulating transition to the power of 0, which should give us the equality. The cool thing here is that we are still working in this locale context, and that we still can refer to the original and simulating transition that is, so to say, in place, but which can be later be any such relation by just interpreting this locale. But while we are in this locale context and prove things under the assumption that such two relations are given, we can already take the locale and specialize it to other such relations, right? So we have our, so to say, current, original, and simulating transition, which is denoted by this arrow and this arrow. And then here we say we make a particular interpretation where this is now, for this interpretation, the concrete original, and this is the simulating transition, and these are derived from the actual ones, so to say. So we say, okay, we have an interpretation, call it shortcut, and this is an interpretation of the simulation system locale. And the original and simulating transitions are just the current ones to the power of 0, which should give an equality. But I wrote it explicitly to make clear it's about doing 0 steps now instead of 1 step. And then we prove that the unilateral progression of this concrete interpretation, shortcut dot unilateral progression, is just the inclusion. And then after having done that, I also proved that the bilateral progression is the inclusion. And this can be done by some automatic reasoner using certain definitions. So, and this just makes it formal what I have just described informally. And this notepad allows us to convey this idea to the reader and show, okay, Isabel has checked it. It's just that we don't want to preserve these statements, this one and this one, for the future to be used. It's just for educational or informational purposes. So, any questions so far?
Yes, one question. The instantiation of a simulation system in the notepad begin end. When you instantiate the original transition and the simulation transition, does it include all the lemma's definition of your local, I would say, module, or it only includes the definition and lemma you have proved up to this point?
To this point, yeah. Otherwise, okay, you could cheat, right?
Yes, exactly. Could have cyclic dependencies, stuff like that.
So the idea is really that the explicit way to define a locale is, say, locale blah 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 simulation system fixes dum dum dum, and then that's it. And then later you can open a locale context and say, okay, now I prove something for locales. I mean, you can do this with other algebraic structures. You define, for example, what a monoid is, and later you say, okay, let's some monoid be given, and then I prove certain things or define certain things. That I continue with the begin here is basically just a shortcut. I immediately enter the locale context and prove something for locales and define something for locales. And then I can end this, but later I can again go into this locale context and say, okay, now I again assume that I have an origin and simulating transition and prove maybe something more in some other theory. But the point is that at this point already, where the cursor now is, we see that the locale is established. So it's shown below here. And everything else we do is just adding definitions and lemmas to this locale context. And these are in place, but everything that comes later in the file is not yet in place. So when you interpret the locale here,
up to this point,
what has been established so far.
One last question is that when you specify your local with the original transition and simulation transition, is it possible to also express properties on the instantiation we'll specify? Or it's not?
So there are two things possible. So first, it's possible for a locale to say there must properties in order for this being a valid simulation system. So it's just that in this case, we don't impose any properties, but you can, for example, define it. It's the common case. Okay, a monoid has this and this operation, and these must fulfill these or these properties. Then when you interpret the locale, then you have to prove the properties in order
to...
And this is exactly what this dot is about. The dot is a primitive proof that doesn't really prove anything, because if I put the cursor here, then I see there are no sub-goals, because nothing is to be proved. And the proof just, the dot just concludes this proof, let's say. But in general, you would have to prove something.
Okay.
More questions? So then maybe let's go to, so now that we have done this, let's go more to the particularities of respectfulness. So first, I have proved here a small lemma about this shortcut progression, which we will need later. So there are others. This is a kind of preservation lemma. There are other preservation lemmas, but these are so trivial that they can always be handled by the automated prover. So my policy here was that there are lots of simple lemmas about certain core constructs that I didn't want to spell out, because most of them are obvious for the human reader, and I wanted this development also to be nice to read for the human reader and not bore the human reader with trivialities. So whenever such simple statement like this was not needed as an extra lemma, because if later we need it, we don't maybe need to specify it explicitly, but the automated prover can, so to say, automatically prove it on the fly in a sense, then I wouldn't state this explicitly. This wasn't the case for this one, so I had to state it explicitly. And this is already actually some very interesting and important one, which will, I think, be important for proof that we have later. So this says, okay, assume we have two sets of relations, this calligraphic K and calligraphic L. Yeah. And we know, and now the quantifiers are important, for all K in this first set, there exists an L in the second set, such that K progresses to L, then the union over this calligraphic K progresses to the union over the calligraphic L. So maybe let's go back to our diagram, and now let's not consider this shortcut progression, but just maybe just a simple unidirectional progression that already becomes clear why this is, maybe. So now let's assume on the left we have a union of relations K, and on the right you have a union of relations L. Then what does it mean for P being a relation with Q via this union? That this means that one of these Ks in our set relates P and Q, at least one. And if we can show now that no matter what it is, for all K in this union, if there's this relation, then we can progress to some L in this other set. And we know that we can progress to the union because each L is included in this union. So we have the progression from the union to the union. So important, no matter in what K of the many Ks on the left, our P and Q are, we can progress to some L so that the P prime is in relation Q prime via this L. So we can pick any, that's good. Questions? So this is important thing, and this hopefully intuitively holds for the simple progression, the unidirectional progression, but then from this you can derive it for the bidirectional progression. And of course also for the inclusion, because it's just a concrete progression, and then also for their conjunction, or this meet here that we had here, right? And so in the end we have this holding for the shortcut progression, which is a bidirectional progression by definition for the actual transition relations and the shortcut relations, the equality-based ones. And the nice thing is Isabel can prove it by invoking just two automated reasoners. And so there's no explicit proof that we have to spell out here. So respectfulness, the definition is what we had. And now first there's some technicalities. So what we will do now is to establish these basic lemmas with which we can prove that certain relations, certain functions on relations are respectful. So, and first of all, I defined some little support for automation. I don't want to get into this stuff from here to here, because this just says that if we have established lemmas about respectfulness, we can mark them with an attribute respectful, which I have introduced here. And this means that they can later be automatically considered when proving the respectfulness of a function. And what I have ultimately done, I have introduced the proof method respectful, which is kind of what's maybe tactic in Cork, that you can invoke, and it will automatically.
It's a kind of generic proof.
Pardon?
It's a kind of generic proof you introduce so that you can use it afterwards on instantiation of F.
Yeah, so technically it's actually a kind of a program that generates proofs, right? That it's an automated prover that finds one proof if it's successful for the concrete statement. And just maybe very shortly, this is just basically a macro using existing proof methods. You can extend Isabelle with new proof methods by going to the ML level and using the ML programming language to implement your proof methods that find these proofs based, so with access to some API that gives you access to goal statements and all that. But this is not what I'm using here. I'm using here an extension called Eisbach, which is basically like a little programming language for defining new proof methods. And this is just a combination with certain operators, alternative and repetition, using existing proof methods, intro, elim, and simp. So simp is this simplifier that automatically does term rewriting. And here it's only used to prove some trivialities, actually. And intro and elim are very primitive, very simple proof methods, namely such that you give introduction or elimination rules respectively, and it just tries to apply them. And here I give some pre-existing rules from the standard library, and this respectful, which is later the list of all the lemmas that I have marked with respectful. So it's a dynamic list of facts, and whenever you establish a new lemma, mark it respectful, then it will be added to this list and be considered by the proof method respectful. So this respectful corresponds to this attribute here. It's in the end a fact list that you build by marking these lemmas. And this respectful on the left is the name of the proof method that you can invoke. So it's two different namespaces. Okay.
Why do introduction and elimination rules have two arguments?
You can pass several rules to consider. So it's a bit automated in that it will check which of the rules can be applied and will also try to reply introduction rules as often as possible.
Okay, so this is more of a list of introduction and elimination rules. Okay.
So here on the top, I have these operators to combine these proof methods. This is alternative. You can try any of them in the end, and this is repetition. And an alternative and repetition is already kind of built to the intro and element methods. There are several facts to consider, and it also tries to apply them as often as possible.
Okay, thanks.
So now we come to our basic statements of what respectful functions are. These functions that have this preservation property here, you saw. So first we have this constant bisimilarity is respectful lemma. And constant bisimilarity is just a function from relation to relation. So it has the type that these functions f must have. And I write it like this. So the bisimilarity in brackets, and this is just the function constant bisimilarity, right? So in Haskell, you would write const bisimilarity. There's no const function in Isabelle Hall predefined, so I write it explicitly as a lambda term. So what does it mean if we look at our diagram here? It means, well, k progresses to f of k, the thing that we have to prove, now means k progresses to bisimilarity, right? So in this simple function f, the goal that we would have to prove would be when we are on relation k and can transition on one side, we can transition on the other side and get into bisimilar processes. And this is kind of trivially okay for an up-to proof, because then we have performed the simulation game one time and are already in processes P prime and Q prime that we know are bisimilar, right, in this largest bisimulation relation. And of course, then we can go on with the bisimulation game based on what bisimilarity means, based on the definition of bisimilarity. So in this case, really, the new processes, the relationship between the two processes, f of k, has nothing to do with the k. And that's an important case for two reasons. So the first thing is that if you have a transition system, a simulation system where the original and simulating transition relation are the same, then bisimilarity is provably reflexive. Bisimilarity is reflexive. So if we use this up to constant bisimilarity, we have to prove that P prime, Q prime are bisimilar, and because its bisimilarity is reflexive, it's, for example, enough to show that they are equal. And this is a case that we have in certain situations. For example, if we have two processes that can both execute a receive action in our process calculus later, and we know if they have received the same thing over the same channel, then they will end up in the same state, in the same process, right? And then, of course, they can simulate each other because they are equal, right? So this is a case that we sometimes have, and for this up to constant bisimilarity is important. And there's another reason why this is important, because there's this famous up to method, up to bisimilarity, and it means that P prime and Q prime don't have to be in relation K, but they must be bisimilar to processes P double prime and Q double prime, which are then in relation K. So the relation to which we progress is basically simulation composed with K composed with simulation, this one. And we will soon see that the composition operator on relations preserves respectfulness. So if you know that constant bisimilarity is a respectful function and the identity function is a respectful function, which we will also see soon, and we know that composition preserves respectfulness, then we know that this is a respectful function. So we know that up to bisimilarity is sound. And that's kind of cool because we don't have to directly prove that up to bisimilarity is sound, but we prove this much simpler thing, that constant bisimilarity is sound or is a respectful function, and then we prove this that respectful functions are sound in general, and we prove this for the composition and so on. And from this, the respectfulness of this up to bisimilarity proof method follows by clever, or maybe not so clever, but obvious composition. So up to bisimilarity is not a fundamental concept here, but it's a derived concept. Okay. So constant bisimilarity is respectful. So if you show that we progress from K to bisimilarity, then we have shown that K is included in the bisimilarity relation. So processes that are relation K are bisimilar. Also, identity is respectful. So this is quite clear, right? So if K progresses to L, then identity K progresses to identity. It's the same, right? It's just using the definition of identity. This concept by similarity is respectful is actually a bit more complicated. It uses our lemma that bisimilarity is a bisimulation. Why does it work? Well, ultimately we have to show this here, right? And now f of k is bisimilarity, and f of L is also bisimilarity, right? So what we must prove in the constant bisimilarity case, that if k progresses to L, then bisimilarity progresses to itself. But progressing to itself means that this is a bisimulation relation, right? This was how this was defined. right? K progresses to itself, right? So if bisimilation should progress to itself, this bisimilarity, sorry, this tilde, right? If bisimilarity should progress to itself, it means that it must be a bisimilation relation, but this is something that we have proved already earlier here, right? So and this is what we are using here. And otherwise, it's again just applying simple proof, automated provers, because it's so trivial, we don't have to spell it out. Another one that still works with simple provers, function composition is respectful, by which I mean function composition preserves respectfulness. I don't know if the name is, I chose this naming scheme. So the concrete function composition of f and g is respectful, but only provided that f and g are respectful. It's really preservation property, right? Yeah, and why does this hold? Well, okay, it means we know that from k progresses to L, we know that fk progresses to f of L, right? And also for any k and L, if we have this progression, we have gk progresses to g of L. And then we must prove that from k progresses to L, we have f of g of k progresses to f of g of L. But this is kind of clear, maybe. No, that was not what I was after. Because we can reason like, what was the shortcut for this arrow? This one, right? So if you have k progresses to L, then because f is respectful, right, we know that f of k progresses to f of L, right? However, G is also respectful. So for any k that progresses to k and L, where we have this progression, we know that G of k is progresses to G of L, but k and L can now also be this fk and this fl. So we know from the respectfulness of G that if fk progresses to f of L, no, we have that G of f of k progresses to G of f of L, right? So if f is respectful and G is respectful, then this composition of f and G is also respectful, because ultimately we can conclude from k progresses to L that GFK progresses to GFL. This is not really what we wanted. We wanted to prove that f of G of k progresses to f of G of L, but of course it's analogous. So composition preserves, function composition preserves respectfulness. And that's also trivial enough for Isabel to prove directly.
Sorry, you wanted an alternative. You might want to say that respectfulness is invariant under composition.
You mean a relation composition?
Yes.
Exactly. This is also what we want. So, and maybe you remember, we had this chain relation, which I said it's just lifted composition, right? And
sure,
this is the one that we want to preserve respectfulness as well. However, I think, yes, this is something that we cannot prove at this point, because it does not hold for general simulation systems where the original and the simulating transition can be different. But it does hold for transitions where they are the same.
Yeah, you wanted, I think that when you were explaining this, you said that I don't have an alternative naming for it. and I was just suggesting the naming. I said that.
Okay. Now I get it.
Yeah.
I mean, so this is the same property as that, for example, in a monoid or something, the product of two things still remains in the monoid. Or you could also say that that respectful functions form a category on, I don't know exactly what the objects would be, but
No,
Yeah,
they're
they're close.
actually, right? Identity is respectful and composition is respectful. Yeah, it's a monoid. And in that, it's of course a category with one object, right?
yeah, but maybe I don't know. Is there a I don't know what the object in the category would be, but maybe there's a nice category that actually.
Yeah, but actually they are monoid, so you can just take one object. I don't know if you can be more specific and look at certain properties of this function and get a richer category, maybe, but I'm not really sure.
As soon as
okay, I think I know what you are after. So if you have the original and the simulating transition to be different, then maybe these could be the objects. Yeah, I think this might even work, because the problem is with the composition, right? You say, okay, k progresses to L implies g of k progresses to g of L, and then from this you must conclude something. And no, I don't. I'm not really sure. Maybe you can get a nicer category if you you can go. No. One moment. No, function composition here. This holds also for simulation systems, right? Where the two relations can be different. So here we just have a monoid, but I think the chain thing, the lifting of the relation composition, this I have proved only for transition systems where both transition relations are the same. But I can imagine, I think it is such that for simulation systems, you could probably prove something like that, but then you would get not a monoid, but a category maybe. I'm not completely sure about this. It's a bit tricky, but it might be worth a look. But it's nothing that I need here, but it's anyhow interesting to look at that there is a richer structure. I had some ideas in this direction, and maybe this was even part of that if you have simulation systems, they can be considered probably arrows or morphisms in a category, and then you can compose simulation systems.
I mean, all those diagrams you draw all look very much like commutative diagrams in a category, but I haven't found a way to make
I think the diagrams as such are not commutative because you have this inclusion. It's not inequality, right?
Yeah, and I mean, it's difficult to know exactly what the objects would be and so on. Like I thought about it for a couple of minutes, but I couldn't really think of a proper way to get all of this out. Like, yeah, here alpha really looks like it would be a natural transformation, but
yeah,
you need functors and stuff, and yeah, I don't exactly know.
At least it's not a proper commutative diagrams because of the inclusion, but of course what you do have is that you can treat the K and L as objects, and then the progression if you have the progression, then you can say, okay, I have an arrow from K to L, so this is what you can do. I think at least they can be done slightly more using category theory than I've done here, but I didn't need it, and I must also say formalizing stuff from category theory in Isabelle Hall can be tricky, I think, because I don't know because Hindley-Milner plays a role. You only have Hindley-Milner types. I don't know if this plays a role, but what could play a role here is that the simulation systems, they are not a kind of first-class entity. These are not values, right? These are local interpretations, the concrete one. I don't know if this makes it tricky. Maybe it can be kind of nicely phrased, but
I've heard that doing category theory in Isabelle Hall is more difficult than with like dependent type theories. But
Yeah.
I don't know Isabella. I only know that series.
Well, you only have Hindley-Milner typing, right? No higher kinded type even. And so far, in the previous calculus implementation, we had this situation that we actually wanted to model monoids and functors, but we could restrict ourselves to some special cases or we would basically fix the type parameters of the monotype, the functor type, and we could kind of circumvent the lack of higher support for higher kinded types. So it worked out for us, but we were already a bit at the edge. So, but for this new formalization, there's no problem with being restricted to Hindley-Milner. It works out quite nicely. So it really depends on what you want. So maybe we are already quite a bit over time, but maybe let me finish this section on respectfulness. So you also have the general union as respectful. This is very cool. Not just binary union, right? So if you have a function, this old f, and all the functions, calligraphic f, that are in it are respectful, then we know that the union is respectful. And here, for the first time, we see a really nice ESOR proof. And I will go through such proofs in the future, not today through this because we are running out of time, but just to give you an impression how this looks. So we have here these proof steps, and it's supposed to resemble kind of typical pen and paper proofs. And so we basically say we want to prove that the union over all these things apply to K, progresses to the union apply to L, provided that K goes to L or progresses to L for K and L. And this is again something like what we had here in our lemma statements, that we have these outer syntax constructs like assumes and shows, which corresponds to constructs of our Isabelle pure logic, right? So it's just that we don't have to write everything down with logical formulas, but can make it a bit more human friendly and make it a bit look more like the typical proofs that you see in papers, right? So we have this if we have these conditions for certain K and L, and what's good about phrasing this with these outer syntax constructs is that in the proof it has already fixed the K and L. So what we prove in the end, I can show you, is that for all K and L, which is signified by these question marks, we have that this implies that implies that here. But if you phrase it like this, then for the proof, it will have fixed the K and L already for us. So we prove something for all K and L, but in the proof, we have some concrete K and some concrete L. And we can refer to this K and L. And this is important because we want to mention the K and the L in our statements here. And this premise is introduced as a fact. So we can refer to it at whatever proof step we like. In this case, it's here. And then we prove just this as our goal. So this is our goal that we have to prove here, as can be seen. And then from this assumption here, we can, and the fact that this progresses to L, we can show that for all functions in this set F, we have this progression. So every individual element here is respectful. So we can use this to go from K progresses to L to F of K progresses to F of L for any such F. And then we do some trickery with sets, which I maybe don't want to go through in detail. So what you see here is we have this for all, and this exists that we ultimately get, and then we apply this lemma that I proved earlier this year. There's a for all and exists that was just about this shortcut progression. And we apply this here to go from this statement over the unions, and then we need some small lemma, so to say, and from this we can show our thesis, which is what we have stated here as our goal. That's this one. And then the actual thesis that this is respectful follows trivially. It's just by definition of respectfulness. So this is something like a vague sketch of why this holds. And it's of course, very powerful. It's maybe more powerful than we typically need, because typically we just have finite. I think there might be one case further down where we actually need that. Okay, so if the general union is preserves respectfulness, then of course the binary union, which is a special case, preserves respectfulness. And this is what we have here. If F and G are respectful, then their binary union is respectful. And then you can see, okay, we just proof this based on this more general statement. So we say, okay, if F is respectful and G is respectful, these are the assumptions, the assumptions. You can see it here, what we have stated as assumptions here. Then we know for all H in the two-element set, FG, we have that this H is respectful. And this is then a proper premise for this lemma here, right? This has this shape of this assumption. So we can directly conclude that the union, the general union of this two-element set is respectful by the fact general union is respectful that we have proved here. And from that follows that the binary union is respectful just by the, this is the thesis. Thesis is what we want to prove here, right? This one. And this, of course, just follows by the definition of, or by the relation of the ship between the binary union and the general union, that the binary union is just a general union of a two-element set. And this is what the simplifier considers automatically and can prove directly. And finally, also the dual of a respectful function is respectful. So what was the dual? It was this thing here, the dual of f, saw this pretty much at the beginning, is a function on relations that takes any relation k and first forms the converse, then applies the function to converse, and then converses the result back, right? So in the end, what's left, what's right is the same, but the point is that the function is not applied to the k directly, but it's in this conversed world it's applied, right? And my thing is also conversion, also this dual construction, this is double conversion, preserves respectfulness, and that's kind of trivial. And why is this? I think this has to do with the fact that our respectfulness is defined based on shortcut progression, which is a bidirectional progression, and this bidirectionality is what makes this work. I guess I would have to think about it again if this is really true. Maybe it's even more trivial, but I think that's the likely thing. Okay, and maybe that should be it for today. And then the next time we can go to up to methods, which you make heavy use of this notion of respectfulness. In particular, we have this key theorem that up to is sound, which means that if our function f is respectful, and we have proved that relation k is a bisimulation up to f, then we can conclude that this k is included in the bisimilarity relation. So basically meaning respectful functions are sound for the sake of up to proofs. Okay, any questions? Okay, if not, then let's conclude, and thank you for listening, and hope to see you all next time when we actually look at the up to methods. Okay, bye-bye.
Thanks, Wolfgang.
Thank you, Wolfgang.
Thank you very much, Wolfgang.
Have a nice
Thank
weekend,
you.
everybody.
Have a nice weekend.
Bye.
Bye-bye.